Okay, welcome back. Sorry for the delay. Get my paperwork here. Just a couple of quick announcements or comments. I will have the lab I have it here as we speak. I've only got a copy of it for the one on Friday. So I'll have it uploaded once we're done here. Give you some time to read it. It'll be PDF format. Basically, I'm going to do some demos to demonstrate some things, and then you guys get to do a separation of a mixture, not a complicated mixture, right? It's a fun lab. All right. Any questions, comments, concerns? Oh, glad to see we almost have a full house here. Almost. All right. Spring break's coming up here pretty soon. Okay, well, we were finishing up on, let me show you the screen. My notes show me that we ended up on this particular page. We have been talking about Lewis dot structures. We had just finished doing the Lewis dot structures for a variety of different compounds. Excuse me. A recap on these is that one, you'll be given a formula shown here on the left. You'll be told who the central atom is. And so that is the atom that everything else is bonded to. And then from there, we identify how many of each atom we have in the whole compound. From that information, we go through the periodic table, determine the number of valence electrons that we're working with. And from that information, we tally up. I tend to convert that to pairs. Tell me how many pairs of electrons I work with. Take the central atom, bond all the atoms that are given to you, and then create a line to bond them. And then going through my counting, if you will, of the valence electron, making sure that whatever I come up with, if I come up with 10 valence electrons, that is what I have to work with. No more, no less. This is because that's governed by the atoms in the compound. And then a lot of times they come in handy as far as you have sufficient number that you can put a bond around all the atoms. And so that everybody has an octet of electrons around it. For example, except hydrogen. Remember, hydrogen always only have one bond, 2 electrons. Its specific rule is the duet. Okay. Now, if we look at here around fluoride, if we look at this bond right here is shared between the fluoride and the chloride. So therefore, it counts as 2 electrons toward the fluoride and toward the carbon. So there's 2 electrons there. And then we have 6 of them around the fluoride. We got a pair there, pair there, pair there. And so there are a total of 8 electrons. Don't forget that line represents 2 electrons. Okay. There's a total of 8 electrons around that fluoride. And the same is true for all the other fluorides. If we look at the carbon, there are 4 bonds around carbon. Each line represents 2 electrons. So there are 8 electrons around carbon. So its octet has been fulfilled. And then hydrogen is sharing 2 electrons with a carbon. Okay. So its duet is fulfilled. And remember, hydrogen always would have just 1 bond. And that's it. So once we do that, we bond everything together. We then identify, making sure the octet is fulfilled. Then we identify the general formula. Remember the general formula A, B, sub X, and E. Okay. What that does is tells us from the general formula what type of shape it has. So for this example, with the one I've been marking up here, we have A. Okay, B represents a number of atoms bonded to the central atom. And in this case, we have 4 atoms bonded to carbon. So that X becomes 4. We don't have an E here. There are no lone pairs in the central atom. So our general formula becomes AB4. With that information, we go to the shapes table. And from the shapes table, we're able to discern one moment, please. I thought I had the shapes table, but I need to load it up here real quick. Okay. AB4, so then we go to the shapes table. In this scenario, we just did is AB4 general formula, which then gives us the geometry. Note that center atom could represent the carbon, and then we had the 3 fluorides bonded toward the central carbon, and then hydrogen up on top. So we have the name being tetrahedral, and then the bond angle between moieties that are bonded to the central atom. And this case is 109.5. The tetrahedral tends to be the most common configuration we find, and then there's deviations from that. So, with that information, going back to the Lewis dot structures, we come to this, we figure out geometry and the name for that geometry. Okay. And that's what we did with all these other ones here. Now, when we start talking about polar compounds and polar bonds, the importance of making a Lewis dot structure come into play here, because sometimes where we need to determine the polarity, what we call the polarity. Think of it for right now, if it's water-like or oil-like. Okay, we'll have more detail in a second. So things that are more soluble in water are polar, because water is extremely the most polar solvent we have. Then you have examples of oil-like or non-polar. Okay, so oil is a non-polar example of a non-polar, and water would be a polar. Now, to determine the overall polarity of the compound, there are times that we need to first draw the Lewis dot structure and then identify certain features about it. So we need to learn how to write the Lewis dot structure. And with that information, then it allows us to define the polarity, if you will, of that compound, whether it is polar or non-polar. All right, so now, this was a summary of doing the HCN. A quick review using the number of electrons that we have, and then going through the inventory of checking to make sure the octet has been fulfilled. If you find yourself that some atoms don't have 8 electrons, then what you start doing is you start making double bonds and triple bonds. You share electrons, but in this case, the nitrogen has an electron, and we create a double bond there. And then from that double bond created, we check to see if the octet has been fulfilled for carbon. If it's not, we go on and make another bond to create a triple bond, like it was done right here. Okay, this triple bond is shared between the carbon and the nitrogen. Okay, and there's the octet has been fulfilled for everybody. Okay, when you do write a structure and you see that you don't have enough electrons for some of the atoms, you don't just arbitrarily add electrons. You have to work with what you calculated, the 5 pair of electrons. That is what you have based on the atoms and based on the valence electrons that every atom brings through the table. Okay. All right. Any questions to this point? Because now we're going to use the same procedure to create structures of what are called polyatomic ions. And you may ask, what are polyatomic ions? Well, I'm glad you asked. Where'd it go? Bear with me. There it is. Okay. From the periodic table, you will find down in the bottom left corner a table, another table within the periodic table, labeled most common polyatomic ions. We're going to use these quite a bit. Now, what they are they're ions. They have a charge on them. They are actually covalent compounds because they're made up of nothing but nonmetals. But being the nature of the beast, they end up with either a negative charge or a positive charge, either a cation or an anion. Okay, and they are a unit. They stay together as a unit. So, for example, if we ever need multiple nitrates, okay, we would put a parentheses around the NO3 and then use a subscript to tell us that, let's say we need two of them for whatever reason, and it's bonded to some compound X. And if we need two of them, we use a parentheses. We don't separate them. We don't just double up the nitrogen and double up the oxygen, but that is the unit. It has its own specific name. That was called nitrate. Then you also have a nitrite. And the same is true for the sulfur, oxygenated sulfur, the sulfate and the sulfite. Okay. And then we have over here cyanide, acetate, the hydroxide. Most of the majority of them are all negative charge. They're anions. There's only one example that we utilize a lot is the ammonium ion. Okay. And this one here you should be maybe familiar with, the bicarb, aka baking soda. Okay. And these are all ions. And we're going to use the procedure to write polyatomic ions, Lewis-Dot structures for these polyatomic ions, okay? The one exception to the change is this. We have to identify whether it's a positive ion or a negative ion, okay? And then we add or subtract a value, a number, one that represents the charge. So if it's a positive one, we're going to either add or subtract one, or it's a negative one, add or subtract one or two or three, whatever it takes. But notice some of these polyatomic anions have a negative charge. Some have just one negative charge or a plus -2. Okay, so let's do an example. Let's go back. Let's talk about the steps. The first steps are the same. We identify the number of atoms. We identify how many valence electrons that they have. And where they differ, we either add or subtract. Now, if they're negative, they're anions, okay? And they have a -1 charge or -2, any negative, we subtract, we add the corresponding charge. So a -1 will add a +1, -2, +2, etc. Okay, it's kind of counterintuitive if you think about it. It's a negative anion, but we add a value. Okay, and the counter is if it's a positive anion, we subtract. Okay, we subtract. Now we're not actually subtracting electrons or anything like that. The electrons are there, except we have to account for the fact that now they're being tied up or they become lone pairs, which we did count, if they were neutral species. Okay. So we're not, in essence, adding or subtracting. Once we come up with a structure, like you did for the neutral compounds. We put a bracket around the whole picture, and then our charge in the upper right corner. Okay, so let's try ammonia. The ammonium ions. Okay, so we do what we've been doing. Okay, we have nitrogen. Okay, there's one nitrogen, and we're going to multiply it is in group 5. So we have a total of 5 electrons. Okay, hydrogen, we have 4 of them, and each one brings a plus a 1 charge, 1 valence electron. So we have 4 valence electrons. Now notice here, if you're at this point and you add those numbers, guess what? You end up with an odd number. So that should be a flag to tell you, because remember, the number of valence electrons that we're going to end up with are always going to be a number divisible by 2. Okay. And so that's telling you, okay, what do? Do I subtract or do I add? Well, in this case, because we have a positive polyatomic ion, we're going to subtract 1 from that value. Okay, so now we have a total of 8, which is 4 pair. 4 pair valence electrons. The nitrogen is the central atom, so we can quickly put nitrogen down. And then there's 4 hydrogens bonded to the central atom. So we go 1, 2, 3, and 4. We bond the hydrogens. Okay, and then it's a polyatomic ion because it's a positive charge. We put the bracket with the charge in the upper right corner. Okay, and so that is the Lewis dot structure for the polyatomic ion called ammonium. Okay, now we can also determine the general formula. So no different than before. So this, we got one, obviously we got a central atom, and then B becomes 4. Okay, so our general formula is AB4. Now, if you go to the shapes table, you will find that AB4 is tetrahedral. Here it is. AB4, which is what we just finished talking about. Notice this will be the nitrogen, then the 4 hydrogens around the nitrogen. Okay, and it being a polyatomic ion, we'll have a bracket and the plus charge around it. Now, you might say, well, what if I mistakenly add a number? Okay, well, let's do that. Okay, so we had said nitrogen brought in 5 and then 4 for the hydrogens, right? Now, instead of subtracting 1, let's say we added 1. Okay, all right, so now we have 10 valence electrons, which is divisible by 2. We got 5 pair. Okay, so then we know the nitrogen is bonded, is the central atom. So we got nitrogen, and then we attach the 4 hydrogens like we've done before. Okay, so that took care of 4 pair. Okay, so we got 1 pair left. If we added instead of subtracting. Okay, now think about it. Where can we put that 1 pair on the structure we just drew? Can we put it anywhere at all? Can we? What do you guys think? I got 1 pair of electrons. Can I put it on the hydrogens? No, the hydrogens are full now. It's happy. Can I put it around the nitrogen? Again, no, because the octet, around the nitrogen is fulfilled. So that if we end up with an extra pair for, in this example, then that, and we can't put that extra pair anyplace, that should tell you, maybe I went wrong. Okay, and then go back and check your math. And also realize that here we're supposed to subtract when it's a positive ion. And what we did was add it, which gave us an extra pair of electrons that at the end we couldn't put it any place. So that's a flag for you to tell you that you went the wrong direction. Okay. So like I stated, it's almost counterintuitive that when it's negative ion, we add the number corresponding to its charge. And if it's positive, we subtract the number corresponding to its charge. Okay. And all right, so here's the example we just did. All right, and there's the formula, there's the bracket, and there's the charge on the right-hand side. Don't forget the bracket because it is a ion. Okay, and don't forget the charge. All right, let's do some examples. Okay, obviously you may not be familiar with these species. That's okay. We will learn them with time. And let's take the first one. Well, we have bromine, which is bonded to 3 oxygens around it. And when we get to the nomenclature chapter, which is the next chapter, we're going to be talking about these oxygenated polyatomic ions that we're going to work with. So we got bromine here. Notice I didn't say bromide because bromine is the central atom, so its name remains bromine. Okay. With 3 oxygens around it, plus a negative charge around the whole thing. This is a bromate ion. All right, so it's a negative charge, so we're going to add, right? Counterintuitive. So we have 1 bromine, it brings 7 valence electrons. Then we have 3 oxygens. Oxygens are in group 6, so it brings 18 valence electrons. And then we add a 1 because it's a negative charge. It's a -1 charge. So we have a total of 26 valence electrons for 13 pair. Okay. So now we have this information, we can do what we've done before. Okay, we know that the bromine is a central atom, so we put that down. There are 3 oxygens bonded to the central atom, so I can distribute them around the bromine and place the oxygens around it, bond them. Okay, well, that took care of 3 bonds, 3 pairs. Okay, so I got 10 pair left to work with. All right, now, it is just my preference. You don't have to do it this way. You can put them on any atom that you want. I just tend to want to work with the atoms on the outside, get their octet fulfilled, and then work my way back in. So starting with the oxygen, I'm going to put 3 pair there. 1, 2, and 3. Now, why would I put 3 pair around this 1 oxygen? Okay. Why couldn't I add more? Oops. Sorry about that. My dog. Okay, why would I put 3 pair around that oxygen and what I just did?
Because there's a little 3 under the oxygen.
Yeah, how many do we have around that oxygen already total? How many electrons? Has this octet been fulfilled? Remember, each line represents 2 electrons. So we got 2, 4, 6, and 8. So the octet has been fulfilled for that oxygen. So I cannot add any more. Let me get rid of these extra lines here. Okay, so I move on to the next one. So that took care of 3 pair. I got 7 pair left over. So I move on to the next oxygen. So I had 3 there. 1, 2, and 3. Okay. And then that takes care of 3 pair again. So I got 4 pair to work with. And then again, add 3 pair to the other oxygen. All right. And so now what I have left over is one pair. Now I do my inventory just because I recommend that until you're comfortable with keeping track of all the electrons. So I keep a number and an accounting of everything so I won't lose track of all my valence electrons. So I got one pair left. Where can I put that one pair that is left over that I have to work with? What do you guys think?
On the outside in the brackets?
Well, no, I got one pair. I got to put it around an atom someplace, but which atom can I put it on?
The bromine?
Exactly. Right there. I'm gonna just make those double dots. Okay. Because I can't add any more to the oxygens because there's 8 around the oxygens. Okay. Before putting them around the bromine, I only had 6 around the bromine. So they're in the logical place. The only place it can go is on the central atom. Now I have 8 electrons around the bromine. 6 of them are being shared with the oxygens, and then one of them is sitting there all by itself, lone pair, not bonding. Okay, so now the bracket, I can place the bracket, and then its charge was a -1, so I can just put it up there. And there is the structure for the bromate. Now the general formula, it would be A. Okay, what about B? What would B be here? How many atoms are bonded to the central bromine?
Can you explain the bracket thing one more time?
Oh, the bracket is only for polyatomic ions. Okay, when we were doing superstar structures for the neutral, we had no brackets. Okay, that's the only difference between the atoms we did before and these atoms. And just to demonstrate, it just shows that the charge is distributed around the whole molecule. That's why we put the bracket around it. Okay, so it's only for the polyatomic ions, not the ones that are neutral, no charge. Okay, so what is B here? How many atoms are bonded around the bromine?
Six?
Ooh, no. How many atoms are bonded around the bromine? Not electrons. How many oxygens are bonded around the bromine?
3.
Exactly, 3. Okay, look at the formula you were given up here. We had the bromine, the central atom, and there's 3 oxygens bonded around the central atom. Okay, now do we have an E? We call that E is a number of lone pair on the central atom. Don't we have a lone pair here? Yes, right there. Okay, a lone pair. It's not bonded to anything. It's sitting on the central atom. Okay, to fulfill the magical 8 number around the bromine. So our general formula is AB3E. With that information, then we take it to the shapes table and look for AB3E, which is right there. Right here. Okay. And so here's the geometric shape, the 3-dimensional model picture of it. Notice that this is the bromine in the middle, and then we have 3 oxygens around it, and the lone pair in the bromine. Then we had a bracket around it to represent the negative charge. Well, the ion inside has this geometry called trigonopyramid, and its bond angle is 109.5. Okay. All right. And there it is. Okay, again, the brackets are used only for polyatomic ions. And these charges on them, on these polyatomic ions, they are distributed throughout the whole molecule. They're not sitting in one particular spot. And so to show that it's a polyatomic ion with the charge being distributed, a bracket is placed around it, and we put the charge up in the upper right corner. Okay. All right. Let's try another one. This is called the sulfate, the SO4 -2. If you look at the polyatomic ion table, where'd it go? Right here, the SO4 is right there. Sulfate has its own particular name. Okay, has a -2 charge. Okay, so remember, is having a -2 charge. What value are we going to add to the valence electron count? How much do we add? As a -2, what do we add? The one we just did had a -1 charge. What do we add? A +1. So if it has a -2, what do you think we're going to add? Any ideas? How about a +2? Remember, we add, if it's negative, we add a number, and that number represents the total charge of the polyatomic ion. So if it had a -3 charge, then we're going to add a +3. -2 charge, we add a +2. -1 charge, we add a +1. It's the opposite for the positive ions. If it's a +1, we subtract 1. If it's a +2, which it's rare, we subtract 2. All right. So sulfur has 6 valence electrons. Okay. And oxygen has 4. So that's a total 4 oxygens. There's a total, and it's in group 6. Oxygen's in group 6A. Okay, so it has a total of 24 valence electrons coming to the structure. Okay, because of the 4 oxygens. Then we're going to add a +2 because of the -2 charge of the ion. Okay, we add that up. We have a total of 32 valence electrons, or 16 pair. Okay. Now we're going to draw it. Sulfur is the central atom. Note that there's 4 oxygens bonded around the central atom, so we can quickly type in here, or write the bond of 4 oxygens around the central atom. Okay, that took care of 4 bonds. So we have a total of 12 pair left to put someplace. Okay, let me ask you a question. Can I put any more electrons around sulfur? The way I've written it right there.
No.
No, I cannot, because there's 4 around it already, 4 pair, which is total 8. So the only place I can put them is around the oxygens, because right now the oxygens only have 2 around each one. So each oxygen is going to take care of 3 pair. Okay, so we just go around the horn, so to speak. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so that took care of all the pairs that I had. I go back and double check to make sure I didn't lose anything and trying to make this formula, the structure. I still have 16 pair. Okay, 12 around the oxygens, and then 4 around the sulfur and the oxygens. Now we draw the bracket and the -2 charge around it. Again, only for polyatomic ions that we put the bracket around. Okay, recall that we did, I think we did methane, and we came up with this formula, CH4. Okay, notice that there's no brackets around there. We also came up with a general formula of AB4. Okay, no brackets around that example because it's not an ion. Okay, ions have a charge, be it negative, be it positive. Okay, so only for that, we put in the bracket and the charge. Now we can determine the general formula, which we have A and B4, which is the same as the one we just did for methane. Okay, many compounds share the same geometric formula. And so now with that information, you take and go to the shapes table, AB4. Okay. And there we go. Shapes table, AB4. And there we are right there. AB4 tetrahedral. Okay. So we got the sulfur in the middle and then the 4 oxygens bonded around it. All right. And we have that. Now notice this one here is CN with a negative charge. If you recall, we did earlier, in the earlier slides, we did the HCN. Okay. And same process. The only difference now is this is called a cyanide. Okay. And this one here, depending, could be hydrogen cyanide or cyanic acid, depending if it's aqueous or not. So this is neutral, no charge. This is a polyatomic ion, the cyanide. We continue with the same process. Okay, 1 carbon has 4 valence electrons. 1 nitrogen has 5 valence electrons, and then we add a 1. So we now have 10 valence electrons, or a total of 5 pair. Okay. And as we did that with this structure, the HCN, where we actually had to create double and triple bond, we do the same here, and we end up with that particular formula. Okay. Where you have a lone pair on the carbon, a triple bond between, excuse me. Sorry about that. So we have a lone pair on the carbon, a triple bond between the nitrogen, and then a lone pair on the nitrogen, and then the bracket because it's an ion. Okay. Notice when we did HCN, it's neutral. We had no bracket around HCN. Let me clear that up real quick. And we came up with this structure earlier. Same procedure. Okay. So this is neutral. This is the polyatomic ion cyanide. Okay. And therefore we needed to use the bracket. Okay. So the takeaway from these polyatomic ions when we draw the Lewis dot structures is that it's the same procedure as we were doing for the neutral species. We tally up all the valence electrons, okay, that each atom brings to the table, to the structure. And then if it's a positive, we subtract a number that corresponds to the charge. If it's a positive charge, cation. And if it's an anion, we add the corresponding number that represents the charge that that anion has. Okay. Okay. Then we continue like we did before. You're going to be given a central atom, put everything that's bonded around to the central atom. Then the last step is not one of the last steps is to put a bracket around it because it is a polyatomic ion and the corresponding charge in the upper right corner. Okay. Then you can do a general formula just like we did for the neutral compounds of ABE, which gives us the geometry of that compound. All right. Which brings us to this particular topic, which we have discussed already, but the chapter kind of wants you to spend a little more time on it. The bottom line is this, okay? They call it valence shell electron pair repulsion, okay? Now, what that means is basically is the following. Let me share something here. All right. Now, if for example, we did ammonia, the structure for ammonia, we came up with NH and lone pair as follows. Okay. Now, when we compare that to say methane, which had this structure here, trying to give it a kind of a three-dimensional picture, if you will. We have carbon in the middle, and then two hydrogens are in the plane of the paper. And then this wedge represents a hydrogen coming out of the plane, and then the hatch mark is a hydrogen going to the back to kind of give you a three-dimensional picture there. Okay. Now, over here, we had the most stable configuration was the AB4 configuration, which was tetrahedral, okay? Now remember that each bond has 2 electrons at each bond. And so these electrons around the four pair are gonna repel each other. And so what they do, they get away from each other, and this configuration is the maximum position they can get where they have the maximum repulsion from each other. So they kind of end up with this tetrahedral configuration, okay? Now, when we start removing one of the pair and removing something that's bonded to the central atom and just leave the lone pair, this following phenomena happens. So here, these 2 electrons, I put it like an orbital there to kind of demonstrate, they within themselves repel each other. There's 2 of them sitting there. And so they're gonna take up more space than they normally do when they are bonded to something like the case on the right, okay? So over here, they tend to take up more space. They repel each other. The result is the nitrogen-hydrogen bonds get crushed in, pushed away, okay? So this bond angle that was 109.5 degrees now becomes much less than 109.5 degrees. So the lone pair have a big effect on the bond angle, also have a big effect on the properties of that molecule on the left compared to the properties on the molecule on the right. Okay, so that's why they're talking about the electron repulsion. If we look at water, we did the Lewis dot structure for water. And if you recall, there are 2 lone pairs on oxygen. Okay, and so that repulsion is even greater. Okay, because now you got 4 electrons, as 2 pair of lone pair on the central atom. So now they really push that bond angle, and that bond angle is much, much less than 109.5, okay? Because the electrons that are not bonded require more space and resulting in pushing the bond angle of the other species that are bonded to the central atom. And that's what the whole thing's about in this particular chapter. The valence shell electron pair repulsion. That effect has a big these electrons that are now bonded in the central atom have a big effect on the properties, okay, of that molecule, which we're going to learn here in a second. Now, basically, we already talked about the shapes table. This is a rehash. We have the general formula of ABE. A is a central atom. B are the atoms bonded to the central atom. They can be all the same or not. They can be different. And then E represents the lone pair on the central atom. Key thing, lone pair on the central atom. We don't care about lone pairs on any other atom outside, just on the central atom, okay? So the classic example of a linear species is all diatomics, for example, or anything when we only have two atoms, its configuration is linear. We really don't have a central atom here because there's only two atoms. To have a central atom, you have the minimum 3 atoms in your compound, okay? So here, regardless of what is bonded to each other, it's by default a linear configuration, okay? Carbon dioxide is an example of an AB2. We did carbon dioxide. It also has a linear configuration. Okay. All right. Now we have an AB3 example where you have basically a flat structure, and there's 3 moieties, 3 atoms bonded to the central atom. Okay. And across the board, we have 120 degrees all the way around. Okay, 120. Okay, so very symmetrical. And if we were to take that picture and just bring it out, you'll see it's flat. All right, that has its name of trigonoplanar. This is a good example of this. This is the structure of formaldehyde. Formaldehyde is a compound that is known to cause cancer. All right, we have the standard I talked about at length, the AB4, that's the tetrahedral. The model on the right kind of demonstrates a 2-dimensional model where the black center atom is carbon and then the white ones represent the hydrogens, okay? When there is a lone pair on the central atom, we end up with the Bent configuration where the general formula is AB2E. Now here's a good example of when looking at the formulas. And if we compare, let me change the color here for a second. This is SO2, sulfur dioxide, okay? And if we look at CO2, carbon dioxide. Now, at first glance, we would think that both of these will have the similar structure, but that's not the case because, first of all, the central atom brings a different number of valence electrons to the structure, okay? And when you work with sulfur dioxide, you end up with this structure with a lone pair on the central atom. So we end up with the AB2E. Carbon dioxide, we did that already. We ended up with a linear species where we had an AB2 configuration, okay? And because of that, because of its Lewis dot structure, we have information now about CO2 versus SO2 with respect to what we call polarity, whether something is polar or non-polar. But more on that in a bit. All right, here's an example of the ammonia that we did where we had NH3, okay? And there's a lone pair on the central atom. And this model doesn't do it justice, but it's not accounting for the fact that we have 2 lone pairs sitting up there in the central atom, resulting in this angle here being much less than 109.5 because those lone pair are pushing the other bonded species in that pairs down, okay? And here we have water. Again, 2 lone pair. Okay, really repelling here, really repelling, causing that bond angle between the oxygen and hydrogen, between the hydrogens to be really much, much less than 109.5. Okay. All right. Let's summarize this. Is given either a covalent molecule or a polyatomic ion, be able to draw the Lewis electron Lewis dot structure, and from that information determine the general formula ABE, excuse me, and using the shapes table determine the shape and the bond angle. Okay, so try these 2 species here at home, the pH3 and ozone. Ozone is its formula is given there. There's 3 oxygens that are bonded together. And tell what we do if you take those home, maybe on Friday, I'll ask again if you're able to come up with a formula, and we'll go through that example. Okay. All right, which brings us to bond polarity. Any question about before we continue?
Can you go back to the ABE slide? Is that a generic formula?
Yeah, the ABE. Okay. The
I don't see that one on our, so we have like the table, and I don't see that one on our like shapes and bonds table.
For the 8, which one? AB what?
It was just ABE.
Oh, there's no ABE. There's ABE2E, like right here.
Oh, never mind. I think I saw it wrong or something.
Okay, yeah, there's always going to be at least 2 B's for at least 1 E. Okay. But the idea of the ABE again is a general formula. A, which always will be there, it's the central atom, and BX and E, I'm just going to call that Y. Okay, where X and Y are numbers from, at the most, X can vary from, if it's just an AB, can vary from a 1 to 4, and E can vary from 1 to 2. Okay.
So A is the central atom. What is B and what is E?
B is always whatever is bonded to the central atom. Notice this is this one here. There's A, and then we got 4 B's around A. Okay. B is whatever is bonded to the central atom. They could be the same or they could be different. Okay. For example, when we did, let me clear this up a little bit. When we did HCN, hydrogen cyanide, okay, we came up with a formula with AB2. Okay. B's are H and N. This is the central atom. A is the central atom is carbon. What is bonded to the central atom is 1 nitrogen and 1 hydrogen. Okay. So B can be either all the same atom, type of atom, or different. It doesn't have to be the same. When we did ammonia, we had A, B, 3, E. In this case, B is 3 hydrogens. They're different. They're all the same. Okay. But it's in generic terms, whatever is bonded to the central atom, that's what B is. And E is simply how many number of lone pair on the central atom. Okay. Does that make sense here? Notice in all these examples, here we got A in the middle, and then we got B bonded to the central atom. A is always in the middle, and then B is bonded to the central atom. Okay,
And the E is the lone pairs.
yes, E is a lone pair. This E is right there. In this case, there's only one E. Okay, down here, E is 2 because there's 2 lone pairs, and B is whatever it is, whatever is bonded to the central atom. Okay,
Okay, I get that. Thank you.
all right. E and but the thing to remember, E is only what's the lone pair on the central atom. We don't care about what's bonded to lone pairs on anybody else, just on the central atom. Okay. Any other questions? All right, so try the pH 3 and then try ozone. Ozone, obviously, there's 3 atoms, 3 oxygen atoms bonded together. Just by that being the case, there's going to be one of those oxygens is going to be a central atom. Okay. All right, so which brings us to bond polarity. We're just looking at the bond. Okay. Which then, from that information, we're going to be able to look at the polarity of the whole molecule. Okay. Now, when we say that a bond is polar, think of it as the Earth. We got a North Pole and a South Pole. The Earth is a polar entity. Okay. A battery is a polar entity because we have a positive side and the negative side. Okay. Now, when it comes to bonding, between 2 elements, we're either going to have equal sharing of those electrons that are being shared. And when we talk about polarity, we're dealing solely with covalent compounds. Okay. Do you remember what we meant by covalent bonds? What was the criteria to have a covalent bond as compared to an ionic bond? What's the criteria for a covalent bond?
It's 2 non-metals.
You got it 100%. So if you got a like a sodium and a chloride, this doesn't pertain because that's an ionic bond. Okay. And with respect to ionic bonds, they have a full charge on a full positive or a full negative. It just, whether it's +1, +2, +3, or -1, -2, -3, it is a full unset charge. Okay. And when they come together, ionic bonds, they just attract to each other like 2 magnets. That's it. They don't share anything. With covalent bonds, what is happening here, electrons, if it's a single bond, those 2 electrons on a single bond are being shared between 2 atoms. And you're going to have either equal sharing or unequal sharing. When you have unequal sharing, you have what is called a non-polar bond. Okay. And in that scenario, I utilize the generic formula of A bonded to A. Okay. Where A and A are both the same atom. And it's a tug of war. Think of polarity or the sharing as a tug of war of those 2 electrons in that bond. In this case, when you have A and A, which are the same atom, there's an equal sharing of those 2 electrons. And therefore, we have what's called a non-polar covalent bond. Okay. No charge, no North Pole, no South Pole. Okay. Now, with respect to unequal sharing, what happens now, you have a polar covalent bond. And I use the general formula of A bonded to B. Okay. And what's happening at that bond there between A and B is one of them is drawing the electron density, the electrons more onto itself than the other. Okay. And that is defined by electronegativity. Now we had talked about EN, electronegativity, before the previous chapter, where electronegativity was a measure of the affinity of an atom that is bonded to another atom to pull electrons onto itself. Okay, so if an element has a high electronegativity relative to the other species, then it's going to pull those electrons onto itself much more than the other. What's going to result is a partial charge, not a full charge like ionic compounds, but a partial charge. Let's say, for example, that the En of B was greater than A. What that means is that the electrons in this bond are being pulled toward B much greater than A, resulting in a more electron density around B. Okay, and we show that by using this lowercase delta symbol with a negative charge that results also in a partial, we call that partial charge. Okay, because B in this example has a greater electronegativity than A, is pulling electrons onto itself more, meaning that there's more electron density around B than there is in A, resulting in less electron density in A, which results in a partial positive for A and a partial negative for B. Okay. We also demonstrate that by using an arrow that goes from A to B, and then the A side's got like a little positive charge on the arrow. So it designates that that's the positive side, and the arrow is the partial negative side. Okay. Now, how do we know which direction that charge goes to? Well, if you recall, when we talked about electronegativity, we stated that fluorine is the most electronegative element that there is. And if we looked at the periodic table, fluorine is in the upper right corner, and every atom here except the every element, I should say, except the noble gases have an electronegativity value. And, yeah, we can go memorize all these values and that's fine, but we don't need to do that because fluorine is the most electronegative element out there. And that's our benchmark. Okay. If fluorine is bonded to anything, then by default, it's going to pull the electrons more onto itself than whatever is bonded to, because fluorine is a lot more electronegative. But if it's not fluorine involved, maybe it's a carbon nitrogen. To determine who is pulling the electrons more is we determine their position on the periodic table relative to fluorine. And whomever is closer to fluorine tells you that's more electronegative. Okay, so if we were to compare, let's say, carbon and nitrogen in a carbon-nitrogen bond, let's say we have a carbon-nitrogen bond here, and we have to determine, okay, which way do I draw the arrow? Well, we go to the periodic table and we look at the position of carbon and nitrogen relative to fluorine, and we see that nitrogen is closer to fluorine. So that tells you that without having to memorize their individual electronegative value, that tells you that nitrogen is a lot more electronegative. And so for that example of this bond, the polarity of the bond means that the arrow will go from carbon to nitrogen, giving us a partial negative on the nitrogen and a partial positive on the carbon. Okay, and that we can do that for any atom combination. Okay, just determine the arrow relative to who's got the most electronegativity, and we use that relative to fluorine and the position of periodic table. Okay. Now this polarity, bond polarity, just is very important in chemistry, because without having that polar bond is difficult to make new compounds. As an organic chemist, whenever we wanted to design a compound or change a compound, put new groups to it or something, we always look for polar sites, because we knew that at those sites, that's where the chemistry can be changed. Okay, non-polar bonds, they're pretty much inert and tough to work with, because there's no positive or negative, and it's all basically nothing. Okay, now the takeaway is this: the simple thing is this: is when we look at a bond, and I use the generic AB scenario where A and A represent the same atom, you have a nonpolar bond. Another example is this: it's a carbon-hydrogen bond. 100% of the time, 100% of the time, the carbon-hydrogen bond is nonpolar, even though they are different. Okay, they are different. They're nonpolar because every carbon-hydrogen bond, their respective electronegativity is basically the same. So for all intents and purposes, there's no difference. And so they're both, the carbon-hydrogen bond could be treated as an AA scenario. The moment you replace one of those A's with anything else, okay, now you have a polar bond, okay? Automatically, you don't even have to think about it. You got two different atoms, automatically it's a polar bond. Remembering that carbon-hydrogen always, even though they're two different atoms, okay, but because of the similarity in electronegativity, always 100% nonpolar. And when we talk about nonpolar bonds, we're going to eventually talk about polar molecules. And this is where you can think of them in terms of oil and water-like. We know that oil and water don't mix. Okay, don't believe me? Take some vegetable oil in a glass, throw some water in there, and tell me what happens. You're going to see a displace. Okay, separation, because oil and water don't mix. Oil is loaded with nonpolar bonds. Okay, whereas water is one big humongous polar bond. Okay, and knowing the bond of a molecule, we can learn to determine whether it's a polar molecule or non-polar molecule, which then tells us some of the properties of it as far as solubility. Would it be more likely to be soluble in water or more likely to be soluble in oil? Okay. And it's all related to the electronegativity. Now, what I want to do is, let me pull up the file real quick. Okay, this is the electronegativity, but before we do that, I need to pull up, gotta make sure you have it here. Okay, on the course website, okay, we have one of the modules is labeled additional chemistry resources. Okay. Excuse me. Now, if you click on, there's a series of what we call simulations. I forgot about the build an atom, but go in there and it'll show you about the protons, neutrons, electrons, and you can play with it and start building different elements. And I'm going to go to click on molecule polarity. Here's a link. I'm going to send you to this. Now select the two atoms. Okay. And what I want to do show you the following. Now, when the electronegativity at the bottom in the yellow and the green, this is where a scale here that can slide and change the electronegativity of the two atoms that are bonded together here, okay? Now, up on top is the scale. On the left is blue that represents positive character, which would be a partial positive. And the red represents more negative electrons, so a partial negative. Now, you can also do it in grayscale. That's okay. I kind of like the color. It's a little bit more descriptive. So the darker the red, the more electronegativity, okay? The darker the blue, the more, let me restate that. The darker the red, the more, yes, the more electronegativity for that molecule, for that atom, and the more electron density around it because it's pulling electrons toward it. So let's take the atom B and slide the scale to the right, and notice the red, B becomes more red in color, and A becomes more blue in color until we can go all the way, pretty red color. Okay, so in this scenario, we have the AB scenario where B has a higher electronegativity. So this example could be like carbon nitrogen. Okay. Like this could be like an example of carbon and nitrogen being bonded together because nitrogen has more electronegative. It is more electronegative than carbon. So the density, electron density in that bond is being pulled toward the nitrogen, in this case, B. Also notice the arrow, what we call the dipole arrows being created, where the arrow itself is pointing toward B, and then the positive side is pointing to A. Okay. Now, once we have a dipole, we can put an electric field around this. Remember the J.J. Thomson, where we had, he was discovered the electron, and he was able to put a plate, electrical field with a positive negative plate, which caused that beam to be deflected. Well, we can do the same thing here because there is a dipole. There's a positive side and a partial positive and partial negative. And if I were to twist the atom, guess what? It rotates so that B is attracted to the positive plate. If the electronegativity of both of them are the same, there's no dipole. The plate has no effect because there's an equal sharing and there's no partial positive side or partial negatives. Only when one atom has a higher electronegativity that we can line it up, if you will, okay? So, see what else I can put in here. Here's the partial charges, okay? So if the electronegativity is the same, what happens is that bond character becomes nonpolar. The moment I change the electronegativity of one atom just a little bit, now it becomes a polar bond. And notice that now I can, even though it's a very small difference, it's sufficient enough to give me a partial positive and a partial negative. All right. So play with that simulation and you can grasp this, because electronegativity just comes back over and over again. Okay, because from the electronegativity of the bonds, and then we're going to be able to determine the molecule itself, whether it is polar or nonpolar, which then gives us even more information down the road. Okay. This is a talk about EN, which I mentioned. Fluorine is our benchmark, and we use that as our guideline to determine if we're comparing two different atoms other than fluorine and determine who's more polar. We find whoever is closer to fluorine is a more electronegative atom, and therefore will pull the electron density toward itself, okay? Obviously, noble gases don't have any electronegativity values because they're happy, if you will. Their octets fulfilled, they're not going to react. Okay, there's the EN trend, increasing from left to right and from bottom up. All of them pointing to fluorine. Fluorine, again, most electronegative. So for nonpolar compounds, all of the diatomic molecules have no fear of isotope beverage. All of them are nonpolar, okay? Because they're the same atom. That scenario is an AA scenario where the two atoms are the same, okay? They have equal electronegativity, okay? So, and here also carbon hydrogen is a nonpolar bond. And because the electronegativity of the carbon hydrogen is basically the same. Now, let me ask you a question. Stating what we just stated here, if I had a Br bond, we agreed that this is a NP bond, nonpolar. But what if I were to replace one of the bromines with chlorine? Okay. Now, that bond, would that bond be polar or nonpolar? Would a bromine chlorine bond be a polar bond or a nonpolar bond? What do you think? Anybody want to take a shot at that? We agree that the BR-BR bond is nonpolar, given that, as I stated, this is an example of an A, the generic formula A bonded to A. Okay. But what if I were to replace one of the bromines with the chlorine, or for that matter, anything else? Do I still have a nonpolar bond? What do you think?
Is it ionic bond?
It's
that?
what?
Ionic bond, or are we not talking about that?
No, not at all. It couldn't be ionic bonds. Remember, ionic bonds are a combination of a metal and a non-metal. Okay.
Oh, these are two nonmetals.
Yeah, this is, and covalent bonds are nonmetals. So if the BR-BR bond is nonpolar because, being diatomic, and the electronegativity of these two are the same, we have equal pull of those electrons, right? But what if I replace one of those bromines with a chlorine? Do we still have equal pulling of those electrons? No, it would be a polar bond. Here you go, Ellie. That is correct. Because in this scenario, we have an A bonded to B. Remember, B, this is the generic formula, okay? Where A and B are totally different atoms and differ just by the simple fact that they're different atoms means that they're going to end up with a polar bond, okay? The fact that when they're in A and A scenario, both atoms are the same, therefore, it's a nonpolar bond. And the way to think about it, another way to think about these bonds is a tug of war. If the tug of war is between two people of equal weight, equal strength, that scenario is an AA scenario, okay? That tug of war is not going anywhere because it's a stalemate. There's an equal pull on that rope. But the moment I take and then that tug of war and I make one person maybe a couple, twice the weight of the other, probably is twice the strength, it is no longer an equal pull now. One, the stronger one, the bigger one is going to pull the electron, that tug of war, over to whoever's the bigger person and the stronger person. So in that scenario, we have an AB scenario. Okay, and that's the point I'm trying to get across is if you're ever asked a question, Is this bond polar or nonpolar? Well, automatically, if they're both of the same atom, it's a nonpolar atom, nonpolar bond. If the both atoms are different, it's a polar bond. Okay. Excuse me. All right. So, where we're talking about polar bonds, we just finished talking about nonpolar bonds. Okay. Now, when one, this scenario is a AB scenario. Notice the examples down here that are giving you. You have a carbon oxygen bond. You know, all of these are the general formula AB. We have carbon bonded to oxygen, two different atoms, polar bond. We have hydrogen bonded to chloride, two different atoms, polar bond. Sulfur bonded to fluoride, two different atoms, polar bond. And of course, the last one, silicon bonded to nitrogen. Again, two different atoms, polar bond. Okay. At this point, we're not asking who's more electronegative. Okay, that's the next step. We first identified that it's a polar bond, and now we identify, okay, if it's a polar bond, who's pulling the electrons? You know, who's the stronger person there? The bigger person is pulling the electrons, and that is a function of who has a higher electronegativity. Okay, so we use the periodic table to help us determine that, with the exception when fluorine is involved. When fluorine is involved with anything and bonded to anything, and we're looking for whether that bond is electronegative or not, then automatically it's a polar bond. Okay. Now, can you see the difference between the carbon fluoride bond versus a fluoride bond? Would you say the fluoride bond is polar or non-polar?
Non.
No, exactly, perfect. Because fluorine in this scenario, they're both the same atom. So there's an equal pull, so we have a non-polar species. Okay. And in the case when we replace one of the fluorides with, say, carbon or anything else, now we have a polar bond. Okay, so the carbon fluoride is a polar bond. And the next question is, okay, which direction are the electrons being pulled? The fact that you're dealing with fluoride automatically tells you, well, the fluoride's winning. Why? Because fluoride is the most electronegative element there is. And so we draw the arrow in this scenario from left to right, giving a partial negative on the fluoride side and a partial positive on the carbon side. Okay. The oxygen-hydrogen bond, again, AB scenario, meaning it's a polar bond. But the question is, which direction? Well, find the position of oxygen and hydrogen relative to the fluorine. You'll see that oxygen is much closer to fluorine than hydrogen. Hydrogen's on the far left of the periodic table. So that in itself tells you that oxygen is a lot more electronegative. Therefore, the tug of war favors the oxygen. And therefore, the arrow goes, in this case, from right to left, giving you a partial negative on the oxygen and a partial positive on the hydrogen. Okay. Now the bond between phosphorus and chloride, you'll see that the chloride is much closer to fluoride. In fact, the chloride's right below the fluorine on the periodic table. So it is a lot more electronegative than phosphorus. Okay. Meaning that the pull of electrons is toward the chlorides, giving you a partial negative on the chloride and a partial positive on the phosphorus, and the arrow goes from left to right. Okay. Again, it's a partial charge. this is the symbol lowercase delta. It's a partial charge. Unlike ionic compounds, and I can't overemphasize, ionic compounds have a full charge. So when we look at the sodium ion, we got a full positive charge. When we look at the chloride ion, we got a full negative charge, okay? That's ionic compound. Covalent compounds, if there is a polar bond, then it's going to be a partial charge because one of the atoms involved in that bond is going to pull the electrons toward itself much more than the other because it has a higher electronegativity. Okay. Of course, noble gases they don't have an EN number, because again, their octets fulfilled, they're good to go. All right, so here's some examples of they wanting you to determine the delta notation, partial negative, partial positive, and the polarity arrow in which direction it's going. So we have a carbon-hydrogen bond here, and what you got to do is what you got to do is first determine which direction. So carbon is a lot more electronegative than oxygen, okay? And that means the oxygen will pull the electron density away from the carbon, giving this partial negative, and the arrow in this case goes from left to right. Okay? The nitrogen fluoride bond, automatically it's fluoride. Don't have to look anything up. It's fluoride, so fluoride wins the tug of war here. Okay, fluoride has the -1 partial negative charge, and nitrogen has the partial positive. Arrow goes from left to right. We did the oxygen hydrogen before. In this scenario, the way it's written, it goes from right to left. Okay, and at times they might write it the other way. You may have the scenario where you have the hydrogen like this. Well, no difference. Okay, we just flip the arrow over. Okay, we got a partial negative on oxygen, partial positive. Okay, it makes no difference how it's written. The dipole goes to the most electronegative element. Okay, so it's either right to left, left to right, depending on how it's written. And then the chloride carbon, right to left, partial negative on the chloride, partial positive. Now, what about the carbon hydrogen bond? Where can I write an arrow here? And if so, which direction does it go? What do you guys think? For the last one. Is that carbon, hydrogen, carbon bond polar or non-polar?
Polar?
Remember, even though they're different atoms, and like 99.9% of the time, when you have two different atoms, you would be correct to say it's polar. The only exception was the carbon hydrogen bond. Okay, that is a non-polar bond. And if you think about it, you might think of all of oils, all the oils. Oil, for example, is non-polar, and that is because oil is made up of a lot of carbon hydrogen bonds, which are non-polar. Okay, and so in this case, we can't write a delta notation or a polarity arrow because there's no dipole and for the carbon hydrogen bond, and that'll be true for any of the diatomic elements, or the have no fear of ice cold beverage, because again, there's equal sharing. Excuse me, equal sharing of the electrons in that bond. Okay. All right. Again, that is the only exception of different elements bonded that are non-polar bonds. Now, we're at this point, we're just simply talking about the bonds. The next step is to take that information and apply it to the full molecule, okay? Full molecule. Let me clear here. This question here, they ask you, what are these bonds ionic? And if they are ionic, then just identify who the ionic bonds are. And then if not, they must be covalent. So if they're covalent, which ones are polar, which ones are nonpolar? So what do you think about the bromine-bromine bond, the very first one? Is it an ionic bond? Refresh your memory. Remember, there's two types of bonds, ionic and covalent. And there's a criteria for each one to identify who's ionic and who's covalent. So is the bromine-bromine, is that ionic or covalent?
Covalent.
Exactly, covalent. So now the next step is, now they identify covalent, is it polar or nonpolar?
Non-polar.
Nonpolar, exactly, because again, it's a diatomic, both atoms are the same, the electronegativity of each one is equal, there's an equal tug of war here. So yes, that is correct. Oh, I went too far. So the phosphorus fluoride, automatically two different atoms. It's a polar bond, okay? We haven't written, we don't have to write, excuse me, you're not being asked to write the notation, but if I had to, the notation would be going from left to right, with a partial negative on the fluoride and a partial positive on the phosphorus, okay? Sodium chloride, by default, it's an ionic bond. It's an ionic compound because we have a metal and a non-metal combination. And then finally, the second one, you have fluoride and bromide, two different elements, automatically it's polar, okay? And if I need to draw the arrow, by default, because fluoride is the most electronegative element, it's going in the direction of fluoride, giving you a partial negative on the fluoride and a partial positive on the bromide. Okay. So polarity is something that happens over and over again. It keeps showing up, and it's going to show up quite a bit down the road. So it's a concept that we need to grasp. Okay. And again, we use the concept of tug of war. It's a tug of war between bonded electrons. When that tug of war is evenly spread out between two atoms, then we have a nonpolar bond. When that tug of war is uneven, because we had two different elements together, and then we have a polar bond. And then depending on who has the more electronegativity, we can determine who has the partial, which is the partial negative side and which is the partial positive side, okay? All right, polar bonds. So given here, they're asking a question, is that ionic, polar, nonpolar bond? Very similar to the previous one. Obviously, we got sodium chloride, by default, metal, non-metal, it's an ionic. HCl, we have a covalent bond, okay? Then we have two different atoms, hydrogen and chloride. So automatically, we got a polar covalent bond, okay? HH, we have a covalent compound, but it's two atoms that are the same. So the tug of war here is equal. So we have a nonpolar covalent bond. Chloride and carbon, two different elements. Okay, automatically we got a polar bond. Okay, we haven't asked anything about which direction we're writing the delta notation, but we'll come back to that. Carbon hydrogen, that is that example, that exception of two different elements that are nonpolar. Okay, so we have a nonpolar covalent bond. We have O2, oxygen, which is two of the same elements. So we have a nonpolar covalent bond. Potassium and oxygen, that's an ionic. We have a metal non-metal combination. Okay. And then finally, the last one obviously is a polar covalent. Okay. Now, if we had to write notations, of course, we would only do it for the covalent compounds, which would be here, the polar covalent compounds, because the nonpolars will have no arrow, no partial. So here we would draw for HCl the arrow from pointing toward the chloride because it's more electronegative. That has a partial positive, that has a partial negative on the chloride, partial positive on the hydrogen. The carbon chloride combination, that will go toward, again, the chloride, okay, with a partial negative on the chloride, partial positive on the carbon. And then finally, down to the last one, obviously going toward the fluoride because it's more electronegative, given the partial negative on the fluoride, partial positive on the phosphorus. Okay, all the others would not have a partial notation or the dipole arrow, only for polar covalent bonds. Okay, now that we talked about the bonds themselves, whether they're polar or not, we're going to take that information and apply it to the full molecule. Okay. All right. So 99.999% of the time, when your molecule has nothing but non-polar bonds, okay, when you have all non-polar bonds, like oils, for example, you have a non-polar molecule. Okay, that's pretty much the whole time. When it comes to polar bonds, it depends. Okay, it depends on the structure of the molecule. We got two examples right here. All right. Now, let's look at the bottom one first. We did the Lewis dot structure of carbon dioxide, and we came up with the structure given down here at the bottom. Okay. Now, notice that when we look at the carbon oxygen bond on the right-hand side, do we not have a polar bond? Yes, it's a polar bond. And that arrow goes from left to right. Okay. When we look at the bond between the carbon and the oxygen on the left, again, we have a polar bond. Okay. And that arrow goes from right to left. Now, the thing about these dipole arrows is as follows. We're not going to, you won't get tested on this. I'm just giving you information about that arrow that helps you to determine whether they cancel out each other. These arrows can be treated what is called in mathematics as vectors. Okay. What's important about that is that arrow represents a magnitude. That distance it has a value, and it has direction. An example would be if I were to give you a vector to go north, I would say travel north 50 miles. Okay, that's a vector. Unlike if I just said go north, well, okay, I go north, but okay, how far? That's not a vector. Or you go 50 miles, which direction? Okay, not a vector. The point about vectors is graphically we can add and subtract them. So for example, if I had two arrows of the same magnitude, meaning the same shape, and they're going in this, and we're going to arbitrarily just assign them 5 units for each one, 5 units, okay? Because they're going in the same direction, their value is cumulative. So what that means is overall, I got 10 units, Okay, they add to each other. Now, if I point one of these in the opposite directions in units, and they are opposite direction, then one is going -5 units and the other one's going +5 units. The result is that I have an overall 0 effect. Okay, because they cancel each other out. And that is what's happening down here with carbon dioxide. The polar bond on the right, its magnitude, because it's going to the right, is canceled out by the polar bond on the left. Okay, and so it cancels out. So the net polar bonds equals 0, resulting in a non-polar molecule. So this is an example of a compound that has polar bonds, okay, that cancel each other out, resulting in a non-polar molecule, which means that it would exhibit more solubility in oil-like solvents than it would in water solvents, okay? Now, and this is carbon dioxide here. Sulfur dioxide, when you do the Lewis dot structure, you end up with that structure given there, okay? It has, in this case, this is for carbon dioxide, it's an AB2, and for sulfur dioxide, it becomes a AB2E, okay? And that's a geometry. Now, if you look at the sulfur oxygen bond on the right, it is a polar bond, 2 different elements. But because of the geometry, notice that the arrow is going, if I needed to put a direction on it, it's going in the southeast direction, okay? Let's assume that this is north and then south, just like a normal north, south, east, and west. The bond on the left, the sulfur oxygen bond, is going in the southwest direction, totally different directions, resulting in that those polar bonds do not, I repeat, do not cancel each other out. That means that SO2, because of the geometry, has 2 polar bonds, and because of the geometry, where the polar bonds don't cancel each other out, results in polar bonds, polar molecule, okay? So see how that works? So the result is this. If, let's rehash for a second. If the molecule has all nonpolar bonds, you got a nonpolar molecule. Okay. If a molecule has polar bonds and the polar bonds do not cancel out, okay, the result is that you have a polar molecule. If the polar bonds do cancel out, then you end up with a non-polar molecule, okay? Polar molecule, if they don't cancel out, non-polar molecule, if they cancel out. And that's related to the geometry. So you can see how the Lewis dot structure is important here, because we wouldn't know that unless, you would think that both SO2 and CO2 will have a similar geometry, but they don't. They're totally different geometry, okay? And we only know that because of the Lewis dot structure. And then looking at the bonds and noticing that they cancel out or not cancel out, then further tells us whether we have a polar bond or a non-polar bond. Let me give you one more example where the bonds actually also cancel out. If we have the tetrahedral configuration, all right, let's say we got carbon tetrachloride. Well, if we do the Lewis dot structure on this, we end up with a tetrahedral configuration. I won't put all the electrons around the chloride, but they would be like that, tetrahedral, okay? Now, this species has 4 polar bonds. Would you agree on that? Yeah, we got 4 polar bonds. We got a carbon chloride polar bond, and there's 4 of them. But because of the geometry, being in the tetrahedral geometry, being tetrahedral means that all four polar bonds cancel out. Okay, which implies that this species is a nonpolar molecule, even though that it had four polar bonds. Okay, because of the geometry, which we wouldn't know unless we drew the structure. Now, if I were to replace one of these chlorides with, say, I don't know, anything else, but we're just replacing it with hydrogen. And now we have three polar bonds and one non-polar bond. The net means the net results in a polar molecule because those three polar bonds are no longer canceling each other out. That one non-polar bond keeps it from canceling out. So we end up with a polar species just by replacing one of those polar bonds. And though I made it a non-polar bond, I could have easily replaced that hydrogen with something else other than chloride, maybe bromide or even fluoride, meaning that, yes, I got four polar bonds, but the magnitude of one polar bond is much greater. That means that the net result overall of the molecule makes it not a polar species, okay? All right. So back to this, and we're going to finish this chapter here in a second, take a quick break, and then we'll come back and continue. All right, so to rehash all nonpolar bonds, we got nonpolar molecule. With respect to polar bonds, if they do not cancel out, if the polar bonds do not cancel out due to the geometry of the molecule, we have a polar molecule. If they do cancel out, then we end up with a nonpolar molecule. Okay, we talked at length about these. You know, CH4 all has nonpolar bonds, so it's a nonpolar molecule. Okay, now PCl3. We talked about carbon dioxide. Carbon dioxide, obviously, you can see they cancel out. Okay, the polar bonds cancel out, so you end up in a nonpolar molecule. The one we can touch on a little bit more in detail is this one, the PCl3. Okay, if you do the Lewis dot structure on that, you're going to end up with this species here with, guess what? A lone pair on the central atom. Okay, so here's the thing. We got three polar bonds, which you would think, okay, we got a polar moiety. But what's happening here is this. A good general guideline for you is this. Whenever you have lone pairs on the central atom, and you only know that by doing the Lewis dot structure, when you have lone pairs in the central atom, automatically that molecule is polar. Okay? Again, because the lone pair takes up more space, and it doesn't give the opportunity for any of the other polar bonds, if it has polar bonds, to cancel out. Okay, so you got a polar molecule, excuse me, whenever you got lone pairs on the central atom. And that's a kind of a general rule of thumb for you to help you out. And the only way to know that, you have to draw the Lewis dot structure and see you end up with a polar molecule. Even the example, even if you didn't know, understand completely about the previous example with SO3, guess what? SO3 has a lone pair in the SO2, excuse me, sulfur dioxide has a lone pair in the central atom. By default, polar molecule. Okay. If you forgot to know about how the polar bonds do not cancel out. The fact that you got lone pair in the central atom, polar molecule. All right, we've done a water, we've done ammonia. Congratulations, you are done with chapter 7. All right, let's take a quick break. Let's go about 2:15-ish. We'll come back. Let me pause. Okay. Well, the next chapter is chapter 8, named nomenclature, which deals with naming of compounds, which reminds me that you have we do have a nomenclature exam, which is worth 10% of your overall grade. Don't forget about it. You have unlimited attempts. The requirement for, at least for SEC, is that you get a minimum of 80%. It's like there's 20 questions, 16 out of 20 to get a minimum of 80% to pass that particular exam. Anything less gets converted back to 0, and you just continue to attempt it. Now, it can have a big effect in your grade or very little, especially if you're on the border. It can knock you down or it can kick you up. At the current time, I don't have any points associated with it, but I will here pretty soon add a 0 to it. Now, I do that for a reason. And let me reemphasize that. I put a 0 in the grade, even though you haven't done it, to give you a true idea of where your grade is, because Canvas, the grade you're looking at through Canvas is only for those that exams that have been graded. Okay, obviously. Now, what was happening in the past, and so I started doing this, was that I wouldn't put a grade in until the last week or so of the semester. Some students continued to not take the exam, totally up to you, but they were under the perception that they were, maybe having an A in their border A or B or C. And then the moment I put that 0 in, because it hadn't been done, the grade drastically dropped. Okay. And then now they only had about a week left to attempt to get that 80% minimum to get the grade back up. And after that, the course shuts down. So to prevent that from happening around mid-semester, probably I'll do it when you guys get back from mid-spring break, I would add a 0 to there if you're not taking that exam, so that you see what effect that does to your grade. And so obviously, as we grade other assignments, your grade goes up, but it keeps in the back of your mind there that, hey, I gotta maybe attempt that exam once or twice, at least to get to 80%. And it's about simply you're given the structure, give the name, or the name, give the structure. Additionally, let me verify this. You have, let me share with you the website again. On the course website, you have a couple of things. There is a module labeled nomenclature test, which has a lot of files in there with respect to nomenclature to help you out. I'm going to go through some of those after we're done with this chapter. But additionally, on the far left, you have something called StudyMate. Okay, if you click on that, this comes up, and you have a link up on top that says nomenclature practice. Okay, click on that, and you end up with an additional program that's interface of Canvas. What I've done is I uploaded, I forget, 140 compound names and structures. It's been a while, and they're in there, and it helps you to help you prepare for naming these compounds. Now, I wouldn't use all of these ones, because this one doesn't understand, like the crossword, it doesn't understand capital letters and spaces. So I would stick either to matching and/or flashcards, and I'll click on flashcards. Okay, so as I click on flashcards, you see, I uploaded 143 compounds. So you have the name oxygen difluoride, and it's asking you to give the formula. So you write the formula out, then to check it, you flip the card, and there you go. There's a formula, oxygen difluoride. Keep in mind that this program doesn't comprehend, doesn't support subscript. So you'll see OF2, that should be a subscript too. Okay. So then you can go on to the next one. You got lead 2 bromide, work it through, see if you got the right formula, and then flip it over, and there you go. There's the formula. So there's one way to help use StudyMate to help you with nomenclature using flashcards. The other way is matching. So what you're given here is the name, lead 2 hydroxide, and then you're asked to select the proper formula. Okay. All right. So that's an additional aid for you to help you out with the nomenclature. It's under, as I stated, StudyMate on the far left corner there. Okay. And don't forget the modules. There are some files under the nomenclature test module, which deal with naming common ions. And like I stated, I will go over those. Okay, any questions about that part?
Let's say you like hit an 80%. Does
Yeah.
it continue letting you take it to get even better grade, or does it kind of just cut you off?
Yeah, that is correct. You have unlimited attempts, and what it does, it keeps the best grade that you have. Now, I go in there because Canvas is not a smart software, and I go in there after you attempt it, and I check to make sure that Canvas gave you the correct credit, and you'll probably find that a lot of times you come out thinking you got a 70. Then I check it because Canvas doesn't understand a multiple of, you may have added a space or something, and Canvas treats it incorrect, and then you'll see that I'll kick it up. But yes, you can continue as many times as you want, and continue to, it will keep automatically the highest score. And then I will also check it to make sure you get full credit for all your answers. Okay. All right, any other questions? But don't forget about that exam. Again, it may or may not affect your grade. It depends where you're at. If you're in the middle and that you're happy with that, then go for it. They used to be, I don't know why, but I fought against it. Is that they used to, SEC, it's not like that in other campuses, but SEC required that everybody pass that exam, or else you didn't pass the course, which was like, deal, stop. My dog over here barking, sorry about that. But no, it doesn't work that way. So, but the compromise was get at least an 80% to get full credit for that assignment. Okay, any other questions? All right, well, chapter 8 is relatively short. We might be able to knock it out. Okay, so here with respect to the atoms, we had talked about this and naming the atoms, they have their own name. Now, with respect to metals, metals, once they become ions, we're going to either, to distinguish them, we would say sodium atom or element or sodium ion. The nonmetals, they're the ones that change their name completely. So sulfur becomes sulfide, oxygen becomes oxide, okay? Be familiar with at least the first 20, and the next group on top of that, Ba for barium, then we've got cobalt, iodine, copper, iron, lead, mercury, silver, gold, zinc, stannous, which is tin. Stannous either be stannous, or you can write TIN, tin. Strontium, nickel, bromine, chrome, manganese, which sometimes gets confused with Mg with magnesium. So manganese and magnesium, and then CD cadmium. Okay, it's the same with silver and gold. The two get sometimes mixed up. Silver is Ag, gold being Au. Okay. All right. So with respect to naming, ionic compounds, remember it's a combination of metal, non-metal. So we have a metal plus a non-metal. The covalent compounds, as we know by now, hopefully, are a combination of non-metals only. Now, the main difference between the two with respect to naming is as follows. With respect to ionic compounds, we don't use prefixes, okay? Like mono, di, tri, etc. With respect to covalent compounds, we do prefixes. Now, what do I mean? Let's do a quick example. So we have MgCl2 versus CO2. So MgCl2 is said to be magnesium, and then it's chloride, not chlorine. It's chloride because the chlorine became the ion chloride. Okay. Now we didn't call this dichloride. Okay, just simply magnesium chloride. This is ionic. This is covalent. Here, the bottom will be carbon dioxide. Okay, carbon dioxide. So remember this, when it comes to prefixes, ionic compounds, no prefixes, covalent compounds, yes on the prefixes. Okay, so we have the monatomic ions, simply the single atom of sodium ion, chloride, calcium. But we talked about this, the polyatomic ions. You go to your periodic table, you see in the bottom of the corner, you will find many of the polyatomic ions that I will show here, but we did talk about those earlier. We'll be using those. The thing to remember about those polyatomic ions, they are treated as a unit. They have their own specific name. We don't change the name. Like PO4, that is called phosphate. It wouldn't be called like oxygen, phosphorus oxide. No, it's phosphate. It's a polyatomic ion. Okay. Now, up to this time, I've been using the term charges. What is this charge? +1, -1. Okay. And really what we should be using, which I'm going to start using, is what is called the oxidation state. Okay. Because, when I say the charge, you were really talking about, the ionic compounds. When we say, for example, what is a charge of the sodium ion? We say, full positive charge, right? But if we look, and we're going to learn how to do this, what is the charge of, say, carbon dioxide? Well, carbon dioxide really has a partial charge simply because it's covalent, okay? And so it doesn't really have, quote, a charge. So we use the term oxidation number when we're talking about either ionic or covalent compounds. It's more descriptive between the two, okay? So with ionic compounds, we have full charge. With covalent compounds, we do have a partial charge. Now, in this case, this carbon, for example, we're going to learn that actually has a +4 oxidation number. Okay, we're going to learn how to do that because each oxygen has a -2 oxide. And there's 4 of them. They have a -4, and that means that carbon must be a +4 to counter the -4 of the 2 oxygens. Okay, we'll learn about that more on that down the road here. All right, so all the elements have an oxidation state of 0. Why? Because they have an equal number of protons, an equal number of electrons. Okay. And once they lose or gain the electrons depending if they're metals or non-metals, then they change their oxidation number. Okay, and so some elements have a fixed charge. There's only one possibility, and this is important here. Okay, because let me pull up my periodic table. All right, shrink it down a little bit. Okay, now, if we look at the periodic table here, and we look at the metals, simply the metals. And then if we look at lithium down, all the way down to number 87, okay. Everybody there is in group 1, okay? Everybody's in group 1. And so everybody there would have a +1 oxidation number. They have 1 valence electron. Your metals, they're going to lose that 1 valence electron, so they end up with a +1 charge. Okay? The next group here would have a +2 charge. Okay, so starting from number 4 all the way down to number 88. Everybody there will have a +2 oxidation number when they become ionic. Now, if you think about it, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 ions. Okay, 12 elements that 100% of the time their oxidation state when they become ions. Okay, group 1, there's 6 of them from group 1 with a +1 charge, 6 of them from group 2 with a +2 charge. Now there's 4 more that are constant the whole time. Aluminum, I'm going to circle them. Aluminum, zinc, silver, and cadmium. Okay, aluminum will always have a +3 oxidation number when it becomes an ion. Zinc will always have a +2. Silver always have a +1, and cadmium, Cd, always has a +2. So we add 4 more to the 16. So we have a total of 16 elements that when they become ions, 100% of the time what their oxidation number is. Okay, what that means now that everybody else, all the other metals, all the way across, all the other metals, whatever they may be, have a variable oxidation number. Okay, variable. For example, copper can have a +1, or it could have a +2 oxidation number. It varies. Okay, it depends. We can't predict that. Those that are circled in red, 100% of the time. And because of that, when we start naming them, we're not going to use what we call Roman numerals. Okay, I'll explain that in a second. So if you have sodium chloride, it's simply sodium chloride. Magnesium chloride, simply magnesium chloride, or zinc chloride, simple, whatever it may be. Okay. All right. I call those a sweet 16 because their oxidation state 100% of the time. 16 elements. All the other ones, the state, all the other metals can vary. And there's an example. Copper could be copper 1, copper 2, totally different compounds. One of them is a blue color, one of them is a green color. Okay, different properties, different everything. The only difference between them is the number of electrons. Other examples could be iron. Iron could be in the state of +2 or +3 state. Okay, so we know that the whole time I've talked about metals, they lose electrons, so they end up being cations with a positive oxidation number. Okay, so as I stated, the alkaline metals, group 1A, always has a +1 and a +2, and a +3 for the metals in the group 3A. Okay, zinc and cadmium always have a +2. Excuse me. Silver always has a +1. Those are the 16 I just mentioned on the periodic table. Okay, that means that all of the other metals, they can vary in oxidation number from a +1 all the way up to a +9. It depends which metal it is. Okay. So the way we distinguish all the other metals, the ones not part of the 16, is we use Roman numerals. Okay. Now these Roman numerals, don't confuse them with the group number on top of the periodic table. Totally different. They're using the same manner of they're using Roman numerals, but the Roman numerals on top of the group, the A metals, that represents the number of valence electrons. Here, the Roman numerals represent the oxidation state of the metal. Okay, and so copper 2, in this example, copper 2 would be represented, if we write it longhand to give its name, we would say copper parentheses Roman numeral 2. To distinguish copper parentheses Roman numeral 1. Okay. Okay, so we got copper +2 here and copper +1. That's how we distinguish the two. It used to be, we used to use the nomenclature of ic versus us, cupric, cupras. It was very ambiguous, very confusing. And so the World Organization got together and said, okay, no more of that. We're going to just assign Roman numerals. There's no ambiguity. So the key to remember is when you see a name of a metal followed by parentheses, that is the oxidation state of that metal. You right there has nothing to do with valence electrons. Okay. All right. So those, the sweet 16, don't use Roman numerals. Okay, because they have a constant oxidation number. And that way everybody in the world knows that is their oxidation number. We don't need Roman numerals. Okay, if you put Roman numerals for that sweet 16, it's incorrect with respect to naming. Okay, here's some other examples. Lead 4 would be written as lead parentheses Roman numeral IV for 4. Iron 3 would be Roman numeral 3. Okay. Okay, as anions, to refresh your memory, are nonmetals that gain electrons and their respective charge, -3 for group 5A, -2, -1. Okay, so let me bring the periodic table back up. You can see here that most of the time we're dealing with these would be a -3. I mean, that's all of them, but we'll be dealing with these two, -2 and -1. Okay, so we got a +1 group down here, +2 group over here, and then we had these, this one, the sweet 16, and these particular anions. So those are the fixed oxidation numbers, okay, for these elements. Okay, so and plus for the nonmetals, recall that we changed the name. So nitrogen becomes nitride, phosphorus becomes phosphide, oxygen is oxide, sulfur sulfide, fluoride, chloride, and bromide. Okay. All right. And of course, group number 8, those are valence electrons. So, excuse me, those are noble gases and nothing, no oxidation number there. Okay. All right. So let's learn. What time is it? We're almost quitting time here. I thought I was going to be able to knock it out. All right, maybe not. So let me stop it here then. Don't want to get too involved with it. So chapter 8, slide 7. Okay, so let us stop it here. And then on Friday, let's talk about the pH, what was it, pH 3 and ozone, as far as Lewis dot structures. And then I should upload, once I'm done here, upload the lab that we're doing this particular Friday. So it'll be a PDF format, so download it, take read it, get ready for it. Basically, we're going to do a mixture. We're going to have a mixture of sodium chloride, sand, and iron. We're going to weigh the 3 different components, and then we're going to separate them, mix them together, and then figure out a way to separate them out back to the original components. Okay, and then I'm going to do some other demos. All right, let us stop it here then.